Hello, we're going to go through the problems that Dr. Poghotanyan posted for midterm 2 review for MA 266. Fair warning, about half of this exam is going to be the last problem. So you'll see what I mean when we get there. Question 1. The particular solution yp of this non-homogeneous second order differential equation is what? So this is exactly the form that we would like to see for using undetermined coefficients. So our guess, we're going to call it YPG, our guess for Y particular is going to be, well, we have 2t over here, so we need a term for t and a term that's just a constant. So we have at plus b, and then plus c e to the t. But careful, we have to make sure that e to the t, or that more specifically 1, is not one of the roots of our characteristic equation. Let's go take a look at that quickly. We have r squared minus 4r plus 3 is equal to 0. This is r minus 3, r minus 1. And there we go. We see that r equals 1 is in fact a solution here. So we are going to need to multiply this c times e to the t by a t. So we have ct e to the t. There's our guess there. And we're going to also need ypg prime. That will be a plus c e to the t plus ct e to the t. And then ypg double prime will be 2c e to the t plus ct e to the t. Now all we have to do is plug all of this into our original equation up here, the non-homogeneous version of it, and we will be able to solve for a, b, and c, assuming we've done everything correctly. So we will have 2c e to the t plus ct e to the t minus 4a minus 4c e to the t minus 4ct e to the t. Going to need to make a little more space here. Plus 3y, that will be plus 3at plus 3b plus 3ct e to the t is equal to 2t plus e to the t. This is looking a little complicated at this point, but we can take some of these and make them into direct equations. So collecting all of our terms with t on them, we see that we have 3a to the t is equal to 2t, and I believe, yeah, we have no other a terms. Sorry, no other t terms. So here's an equation for us that gives us a is equal to 2 over 3. Now, taking our constants, we see that we have negative 4a plus 3b, so minus 4a plus 3b is equal to 0. We can rearrange this to say 3b is 4a. We know that a is 2 over 3, so this is 8 over 3, and so b is 8 over 9. Move that over there. Okay. Finally, solving for c, we see that we have a 2c e to the t minus 4c e to the t, so minus 2c e to the t is equal to e to the t. Yes, I didn't miss any of those. And this just means that we cancel these out. 1, c is negative 1/2, like that. And nicely, and this is supposed to happen if we've done things correctly, we have 3ct e to the t plus ct e to the t plus, not 3, plus minus 4ct e to the t. All of those terms go to 0, which is exactly what we want because there is no t, no ct e to the t. Really, this isn't the same t, but there is no constant term multiplied by t e to the t over there. And so we're pretty much ready to solve this. We said that a was the factor on t here, so we can start forming yp. That's 2 thirds t plus b plus 8 over 9 minus 1/2 t e to the t. And so that gives us a as our answer. 2, we're given this second order non-homogeneous differential equation with 2 initial conditions. And we are going to try to find y of 1. So similarly to what we did last time, we're going to make a guess. In this case, ypg is going to be a e to the t, because that's the form that our f of t term takes on the right-hand side. But yet again, let's make sure that our characteristic equation doesn't overlap. We have r squared plus 5r plus 6 is equal to 0. And I can tell you that if we plug in r equals 1, we are going to get 12, which is most definitely not 0. So we are safe here because 1 is not, fix this t, 1 is not a root of our characteristic equation. But that said, I shouldn't have erased that. R squared plus 5r plus 6 equals 0. We're going to need our characteristic solution because we are solving for y of 1, not yp of 1 or yc of 1. So we're going to need these. This will be r plus 2 and r plus 3. So r is equal to -2 and -3. So we know that yc is c1 e to the -2t plus c2 e to the -3t. And we can leave that right there for now. And we shouldn't be worried about these c1s and c2s because our 2 initial conditions will take care of those. So with our guess of a e to the t, the derivatives of that are just also a e to the t. So in total, up here, we're going to get a e to the t plus 5a e to the t plus 6a e to the t is equal to 24 e to the t. This is 12a e to the t. We can get rid of the a to the t's and see that a is equal to 2. So if a is equal to 2, we can take our yc here, turn it into just our y of t, and add in the yp that we found, which was 2 for a e to the t. We know that y at 0 is 0, which pretty much means that 0 is equal to c1 plus c2 plus 2. So we can set up a first line of our augmented matrix. We're about to solve 1, 1, 1, 1, -2, because we'll have to subtract that 2 over to the left-hand side. And then secondly, taking our derivatives, we'll have y prime of t is equal to -2 c1 e to the -2t plus, not plus, minus 3 c2 e to the -2t plus 2 e to the t. So yet again, y prime at 0 is equal to 0. So we can say that -2 is equal to -2c1 minus 3c2. So we can add a line here, -2, -3, -2. So this is our augmented matrix. And solving it, I'm going to flip all of the signs in this row to make things a little easier. Subtract 2 row 1s from row 2. We get 0, 1, and 6. And then subtract here -8. And we are almost done. We can say that y of t now is c1 e to the -2t plus c2 e to the -3t plus 2 e to the t. And so y of 1, which is what we're looking for, is -8 e to the -2 plus 6 e to the -3 plus 2e. and that is right there. Yeah, okay. Looks good to me. Okay. Moving on, 3. We have a differential equation here with 2 fundamental solutions, and we are trying to find y of 2. So whenever we're given 2 solutions like this and we're trying to solve a non-homogeneous differential equation, especially one that's already been put in the form where the coefficient on y double prime is 1, we are going to be doing variation of parameters, where variation of parameters says that yp is equal to negative y1 of t times the integral of f of t multiplied by y2 of t all over the Wronskian dt plus y2 of t times the integral of y1 of t times f of t over the Wronskian dt. And so we can start solving for these individual components and setting up a final computation to do here. So finding our Wronskian, that's just going to be the determinant of the matrix formed by our 2 fundamental solutions and their derivatives. We have t squared, 1, 2t. This will give us AD, the A term, times the D term, 2t squared minus t squared. So our Wronskian is t squared. So let's go in both of these and replace these with t squareds. Additionally, we can plug in all of our y1s and y2s. Our y1s are t, and our y2s are t squared. Additionally, f of t is just this function of t on the right-hand side, and you have to make sure that your equation is in the form where, like we said earlier, the coefficient on y double prime is 1, because if it wasn't, you would have to divide whatever's there out in order to find f of t. But in our case, it's just 2. And we are ready to solve. All of this will cancel out, and we'll have 2 dt, and over here we will have 2 times 1 over t dt. And computing this will be negative 2t squared plus t squared, 2t squared ln t. I'm going to make this look a little better. Plus 2t squared ln t. Okay, and we know that this is yp. In order to find y of t in general, we're going to need to add yc, where yc is c1 times our first fundamental solution plus c2 times our second fundamental solution. And so putting these together, where y of t is just yp plus yc, y of t is negative 2t squared plus 2t squared ln t plus c1t plus c2t squared. Since we're given initial conditions, we can solve for these c1 and c2 components. So let's do that. We see that y of 0, sorry, we're not solving y of 0, we're solving y at 1. That's going to be negative 2 plus this entire term goes to 0 because ln of 1 is 0, plus c1 plus c2, and this is equal to 0. So we can set up the first line of our augmented matrix as 1, 1, 2, because we have to move that negative 2 over to the other side. And now we're going to need to find y prime of t. That will be negative 4t plus 4t ln t plus 2t, yep, plus c1 plus 2c2. Whoops, hope that wasn't too loud. I need to turn my Wi-Fi off. There we go. Okay, so continuing on, y prime at 1, y prime at 1 is 0, and that will be -4 plus 0 plus 2 plus c1 plus 2c2. Solving this, we will have -2 on this side, so we'll get +2. So we're left with 2 is equal to c1 plus 2c2. So that's 1, 2, 2. And so solving this, we see, if we subtract row 1 from row 2, we'll get 0, 1, 0, 0. So c1 is equal to 2, c2 is equal to 0. So coming back to our y of t that we have here, c1 is 2, and c2 is gone. And so I know it's getting a little bit of a jumble in here, but if we're solving for y of 2, that will give us -2 times 4, so -8, plus 8 ln 2 plus 4. So we get 8 ln 2 minus 4. D should be our correct answer. Question 4, we are rewriting the second order differential equation as a system of first order equations. So we can say that u1 is equal to u, and as a result, u1 prime will be equal to, let's call it u2, and u2, remember, is the equivalent of u prime, where u2 prime is the equivalent of u double prime, and so this we can set equal to this equation solved for u double prime. So we can rearrange this to say 2u double prime is equal to cosine of 2t minus 3u prime minus ku. And then dividing everything by 2, we have things in terms of u double prime, which in our system up here is u2 prime. And so expressing this in terms of u, we will have cosine 2t minus 3 u1 prime minus k u1, where u1 prime is the same thing as, or u1 prime is the same thing as, oh, whoops. And so we can express u2 prime as 1/2 times the quantity of cosine 2t. That doesn't change at all. That's just our dependent on our dependent variable t, minus 3 u2, where u2, remember, is u1 prime, which is the same thing as u prime, minus k u1. And there is our system of first order equations there. Number 5, the solution of this system right here is what? So we're going to be using the eigenvalue method, the eigenvector method. I'm actually not sure which it's called, and then solving for our initial condition there. So if we want to find our eigenvalues and then eigenvectors, we're going to be solving the determinant of a minus lambda I equals 0. So that will give us 1 minus lambda, 1 minus lambda, minus 4 is equal to 0. Or lambda squared minus 2 lambda plus 1 minus 4, so minus 3 is equal to 0. This will be lambda minus 3, lambda plus 1 is equal to 0, or lambda equals 3 and -1. So plugging in lambda equals 3 to a minus lambda I, we will get -2, 1, 4, -2, which will simplify down to 2, -1, 0, 0. And in fact, we can make that a little more simplified there. And putting this into eigenvector form, we see that this is really saying that x1 is equal to 1/2 x2 if we move that x2 term to the right-hand side. And so this x1 position will be 1/2, and x2 is equal to 1 of itself. So this is the eigenvector that we get. We can multiply this by 2, and we will get 1, 2, like that. Okay, moving on, we have lambda equals -1. Plug that into a minus lambda I, and we will get -1, so that's 2, 4, 1, 2. We can simplify that down to 2, 2, 1, 0, 0, and this will give us an eigenvector. This will give us our eigenvector. Still need to do this. 1/2, -1/2, 1, -1, 2. Okay, of -1, 2. And so we can go up here and form our x of t as c1 v1, which we saw to be 1, 2, e to the 3t, plus c2 -1, 2, e to the -t. And plugging in t equals 0, we see that 3, 2, using our initial condition up there, is equal to 1, 2, c1 plus -1, 2, c2. We can make this into yet another augmented matrix, 1, 2, -1, 2, 3, 2. Simplify this row down to 1, 1, 1. Subtract row 2 from row 1, 0, -2, 2, 1, -1. Subtract row 1 from row 2, 0, 2. And so we see that C1, we go back to our x of t, C1 is equal to 2, and C2 is equal to -1. And if I remember correctly, this will get factored into our vector there. So we should end up with 2e to the 3t times the vector 1, 2, so we like a and e so far, plus e to the -t times 1, -2, so a is our correct answer. 6, let's solve a prime equals ax, and this is essentially the exact same thing as the last question, except looking at our answer choices, we are going to have some complex eigenvalues to deal with. So the determinant of a minus lambda I equals 0 will have us solving lambda minus 1, I'm sorry, 1 minus lambda plus 1 is equal to 0, or lambda squared minus 2 lambda plus 2 is equal to 0, and running the quadratic formula through this, negative b 2 plus or minus the square root of b squared minus 4ac. This will give us negative 4 under here, so 2i all over 2a over 2. So we have 1 plus or minus I as our values for lambda. And remember, for these, especially when we're making a real solution out of here, we only need to work with one of these eigenvectors and then one of its single corresponding eigenvalue. I said that backwards. One of these eigenvalues and its single corresponding eigenvector. So taking lambda equals 1 plus I, we can write a minus lambda I as negative I, -1, 1. And extracting an eigenvector, let's just look at what this second equation is saying. This is saying that negative x1 is equal to I x2, or x1 is equal to negative I x2. And so we can express this as negative I 1, where really this is a vector of x2, where x1 is equal to negative I x1, x2 is equal to 1 of itself. And so now with this, we will take v1, which we just found to be negative I1, and multiply it by e to the lambda t. And I'll just expand that to be e to the t plus it. And we can take this e to the it, take it out like that, and turn it into cosine t plus I sine t. And with this, we can make our real and imaginary portion of our solution and eventually find x of t as a result. So I'm going to move this up here, and we can continue. So the real vector that we're going to get out of this is going to come from when we multiply sine on the top and cosine on the bottom. We don't want to have any more i's laying around. So the real vector will be positive sine t, because negative I times I is 1, and then cosine t on the bottom, e to the t, got to remember the c1, and then our x of t, got to be clear, and then our imaginary portion plus c2 is going to come from multiplying cosine on the top, so negative cosine t, and multiplying sine on the bottom, plus I, well, we don't use the i's anymore, plus sine t. And with that, we should be ready to solve for, there we go, should be ready to solve for our initial condition that we are given. So x at 0 is negative 1, 2, and that's equal to c1 times cosine t sine t evaluated at 0, so 0, 1. E to the t is just 1, and I forgot our e to the t over here, plus c2 negative 1, 0, multiplied by 1 yet again. So again, here is our augmented matrix 0, 1, negative 1, 0, negative 1, 2. And so we see that C1 is equal to 2, C2 is equal to 1. And so we can go up here, replace C1 with 2 and C2 with 1, and we should be done. I just have to figure out which one is our correct answer choice. It's actually right here. What they've done here is just factored out a negative 1, and instead of this cosine being negative, they just have minus positive cosine minus sine. So C is our answer for 6. 7, let's solve this initial value problem. We're solving x prime equals ax, and we're given an initial condition for x and a. Because we are seeing t's pop up in our answers here, we should automatically be thinking that we're going to have a situation with multiple eigenvalues, or a single eigenvalue in this case, with a multiplicity of 2, where we'll have to go find a generalized eigenvector to actually set up our solution. So finding the determinant of a minus lambda I equals 0 for this will give us 1 minus lambda is equal to 0. So lambda squared minus 2 lambda plus 1 is equal to 0, or lambda minus 1 squared is equal to 0. Lambda is equal to 1 with a multiplicity of 2. So plugging in lambda equals 1, we would hope and pray that we get 2 eigenvalues out of this deal, but we can already kind of tell that we're not going to, because we will get 0, 0, 0, 1, which, since it only has one free variable, will only have one associated eigenvector. What this is saying, if we read this out as in equation form, is that x2 is equal to 0. So x1 is our free variable, and thus that is the eigenvector that we get out of this whole deal. And now we can set up the first half of our equation, but we're still going to need to find our generalized eigenvector to fully solve it. We will have x of t is equal to c1 times 1, 0 e to the t plus c2, and then we're going to have two vectors in here. We'll have 1, 0, our v1 times t plus v2, our generalized eigenvector, all multiplied by e to the t. So finding v2 is going to be our issue here. So finding v2, all we have to do is set up the augmented equation formed from a minus lambda I and our first eigenvector. So that will be 0, 1, 1, 0, 0, 0. And reading this off in equation form, it's an augmented matrix, so this says that x2 is equal to 1. And so if we put that in a little constant vector here, we will have 0, 1, which is our generalized eigenvector there. And now all that's left to do is solve for our initial conditions. So x of 0, we're told, is 1, 1, and that's equal to c1 times 1, 0 plus c2, there we go, times this component will go to 0, multiplying by t when t is equal to 0 is also equal to 0. So we have c2 times 0, 1 e to the 0. So solving 1, 0, 0, 1, 1, 1, we see that both c1 and c2 are equal to 1. So we can get rid of both of those. And then finally, we are ready to solve. And it looks like there are some combinations we can do over here, because this 0, 1 e to the t can just get added to our 1, 0 e to the t, and we can say that x of t is equal to 1, 1 e to the t plus 1, 0 t e to the t. So we have answer choice C, e to the t times 1, 1 plus t e to the t times 1, 0. 8. Let's find a particular solution of x prime equals ax minus 2, 3. So just like in our single-dimensional case when we only have one equation, our guess is just based on what this non-homogeneous little bit over here is. So I'm guessing that our solution will be made up of some vector a and some vector b. And you can go and solve for the solutions over here to kind of, you know, make yourself okay with the fact that this does not overlap with any of the solutions that we get here. But you know, I can assure you, I went through it. We're not overlapping, which is great for us, although we will have to worry about it in our next question. So plugging in a, b prime, well, those are just constants, so we'll have 0, 0 is equal to 0, 1, 1, 0 multiplied by ab minus, whoops, didn't really organize that very well, minus 2, 3. And so we can solve these. We have 0 is equal to b minus 2, and 0 is equal to a minus 3. So we see that a is equal to 3, b is equal to 2. And so our solution vector that we originally guessed was ab is actually 3, 2. So a is our answer. 9, let's find the general solution of this thing right here. So the thing that made these kinds of questions seem incredibly terrible to work through on the homework was the fact that I didn't realize that you can do them separately. you can do all the individual guesses separately. So we can pretend that really this is just a 0, 1, and then work through that problem and find the portion of the particular solution that 0, 1 contributes to things. And then we can work through it as if we only had terms with e to the negative t involved. And it makes things feel a lot less like they're quickly spiraling out of control. So in that vein, let's start working with our constants first. So we're pretending that this says 0, 1. So we're guessing A, B, Y, P, G. Well, really it's X. Our X particular guess is AB. And so plugging that in, we'll have 0, 0 is equal to 2, 0, 1, 1, AB minus 0, 1. And so solving, we see that 0 is equal to 2a minus 0, and 0 is equal to a plus b minus 1. So a is equal to 0, b is equal to 1. And so that gives us half of our particular solution there. So I'm going to write down our xp. We know that xp, one of its portions is 0, 1. But before, I should have done this earlier, before we go and work with our e's, we're looking for a general solution. So we're going to need the solutions to the characteristic. Well, in this case, it's really not the characteristic equation yet, but the non-homogeneous. That's also wrong, the homogeneous equation. So let's get rid of this guy entirely and solve here. So we have 2 minus lambda, 1 minus lambda is equal to 0. So lambda is equal to 2 and 1. Not sure why that was so hard for me right there. So we know that our I'll put it over here, our xc is c1 times v1 e to the 2t plus c2 v2 e to the t. And plugging in lambda equals 2 to a minus lambda I, we will get 0, negative 1, 1, 0. This is saying that x1 is equal to x2. So we get an eigenvector of 1, 1. That's our v1, 1, 1. And then plugging in lambda is equal to 1, we get 1, 0, 1, 0, which we can simplify down. This is saying that x1 is equal to 0, x2 is free, and so we get a vector 0, 1 out of the deal. So 0, 1 will go in for v2 up there. And now that we've found our xc, we've also confirmed that 6e to the negative t will not overlap with any constant multiplied by e to the t. So our guess can just be minus, or well, this portion. There really is no minus. Our guess can be a e to the negative t, b e to the negative t. So taking the derivative of that, we are going to have on our left side negative a e to the negative t minus b e to the negative t is equal to 2, 0, 1, 1, a e to the negative t, b e to the negative t, minus 6 e to the negative t. And remember, since we're doing this in halves, this 1 does not really exist for us right now. So solving, we'll have negative a e to the negative t is equal to 2a e to the negative t minus 6 e to the negative t. That's a 6, minus e to the negative t. There we go. And our second equation, minus b e to the negative t is equal to a e to the negative t plus b e to the negative t, and that is it. We can subtract. In fact, before I do any of that, I'm going to get rid of all of these e to the negative t's because all of our terms have them. There we go. we can subtract 2a over here and see that minus 3a is equal to negative 6, or a is equal to 2, replacing that in here, subtracting a b, minus 2b, b is equal to negative 1. So we can finally add our second bit to xp, which will have 2e to the negative t and negative e to the negative t, like so. And because x of t is equal to xp plus xc, we will have 0, 1 plus 2e to the negative t minus e to the negative t plus c1, 1, 1, e to the 2t plus c2, 0, 1, e to the t. And okay, hopefully that is correct. Put a little bit too much work into it for it not to be. Okay, number 10. A spring mass system is governed by this initial value problem. For what values of omega will resonance occur? I had to dig pretty deep into the textbook to find these equations, and hopefully they are correct. So we know that a spring mass system is expressed in the form of mx double prime plus cx prime plus kx is equal to f of t, or actually they call it f0, multiplied by cosine omega of t. And really this is omega 0, the natural frequency. If we had no damping term in here, the value of w for which resonance would be that natural frequency, but because we have some damping, everything gets thrown off. So we have two cases here to determine what equation to use to find our value of omega m, omega maximum, for which what's that called? The amplitude of our spring over time is the greatest. So this is dependent on whether c squared is greater than or less than 2km. So in our case, c is equal to 4, k is equal to 4, and m is equal to 1. So we'll see pretty quickly that 16 is greater than or equal to 8, so we will use this equation right here. We're taking the square root of k over m, that's 4, minus c squared, which is 16, over 2m squared, which is 2. So 4 minus 8, and we get 2i. And the book never talked about, as far as I could read, what it means necessarily when you get an imaginary value for this omega. I can't imagine that it means anything good. If this was the exam and I got this and I didn't know what it meant, I'd probably just say that practical resonance does not occur for any real value of omega, which is perfectly true. So yeah, there are no values for omega for which practical resonance will occur in this case. If you want to solve this the long way around, the book gives a very big equation to solve for c of omega, which is just the amplitude over time. No, sorry, not over time, as a function of omega. But what you can do is take the derivative of c, so c prime of omega, and solve that for when that's equal to 0, and that will give you the value of omega for which c of omega is maximized. And if you go through that way, you also get the same result, namely that resonance doesn't occur for any real values. You also get 2i. So let's move on. We have 11. Okay, this is the warm-up to the Laplace marathon that's about to happen on 12. We have the Laplace transform of e to the t plus e to the t cosine 2t. And since we know that the Laplace transform is linear, this is the same thing as the Laplace of e to the t plus the Laplace of e to the t cosine 2t. And we know how to solve these pretty easily, although I am going to bring in our handy little table over here for future reference. We know that the Laplace of e to the at is, so the Laplace of e to the t for a equals 1 in this case is 1 over s minus 1. And I'm really sorry if this bugs you. I know it's going to bug some people out there, but I recently have been using, well, I've only known the Laplace transform for like a couple days, but most of that time I've been using alpha instead of s because my 5s look a whole lot like my s's. So this is not a good recipe for me. So I changed that variable. So I'm using alpha. So we have 1 over 1 minus alpha, and that's coming straight from this guy right here. For a is equal to 1. And then additionally, we know that whenever we multiply some function by e to the t, the Laplace transform of that will just be the Laplace transform of the unmultiplied by e to the t function, where we replace all of the t's in the Laplace transformed version with t minus whatever constant is multiplied by t in the e to the t. And so what I mean by that is that this will be, let's see, the Laplace transform of cosine of 2t, which is s, so alpha over alpha squared plus a squared, which in our case is 2, so 4. And then we need to replace all of our alphas with alpha minus 1. And that should be that. And this is actually one of the ones I can very easily check. So I'm going to pause and make sure. Okay, I just checked everything, and this is correct. Moving on to the marathon of a problem that is problem 12. Question number 12. We have y double prime plus 3y prime plus 2y is equal to 4u1 of t. When I first took this exam, I thought that u1 of t was just some arbitrary function u of t, and it just happened to be the first one, maybe of many, but in fact, that's tiny. In fact, this is the unit step function. So what u1 of t will do is for t between 0 and 1, it will be equal to 0, and then at t is equal to 1, it will jump up discontinuously to exactly 1. And in this case, we have 4u1 of t, so that would just jump up to 4. But either way, this function is Laplace transformable because it is piecewise continuous, where we can patch together the entire domain as continuous in pieces, but overall it is not continuous. But that's all we need for a function to be Laplace transformable. And we see over here on our little cheat sheet that u1 of t, the Laplace transform of u1 of t is e to the negative alpha over alpha. And just to warn you, I already told you here, but if you skipped, I'm using alpha. My s's look like my 5s. I like drawing alpha, so here we are. And I should be clear, we are getting a negative 1 in here because we take whatever u of c value that is and take e to the negative c alpha over alpha. So now moving on to all of our derivatives over here, we know that the Laplace transform of y double prime is, the Laplace transform of y double prime is alpha squared y of alpha minus alpha y of 0 minus y prime of 0, and the Laplace transform of y prime is alpha y of alpha minus y of 0, and then just to be clear, the Laplace transform of y is just y alpha, where that's just the way to express y that's in the alpha domain, or whatever you want to call it. So we can plug these three in, take the Laplace transform of both of the sides of our differential equation here, and get something ridiculously complicated that in about 20 minutes we'll have in a form that, well, then we'll have solved. Okay, so y double prime here is alpha squared y alpha minus alpha times y0, well, y0 is just 0, minus y prime of 0, so that's minus 1. And then we have 3y prime, so that will be 3 alpha y alpha minus 3 times y0, which is, again, just 0, plus 2 y alpha, transforming that to y. And then on our other side, we have 4 e to the negative alpha over alpha. And remember, multiplying constants in does nothing, just like multiplying by a constant in an integral. We can take it out because the Laplace transform is linear. I believe that's one of the properties that comes from that. Okay, so before we do much else, let's add our 1 over here and factor out y alpha. So y alpha multiplied by the quantity alpha squared plus 3 alpha plus 2 is equal to 4 e to the negative alpha over alpha plus 1. Now we can divide all of that out and factor some stuff, and we will have y alpha is equal to 4 e to the negative alpha multiplied by the quantity 1 over alpha times alpha plus 2, alpha plus 1, and then plus 1 over alpha plus 2, alpha plus 1. And now we have two partial fractions to compute. So we are going to take 1 over alpha times alpha plus 2, alpha plus 1, and we are going to put this in the form a over alpha plus b over alpha plus 2 plus c over alpha plus 1. So multiplying this denominator into everything, we will see that 1 is equal to a alpha squared plus 3 a alpha plus 2a then plus b alpha squared plus b alpha plus c alpha squared plus 2c alpha. Ugh, God. Okay, so we can equate all of our constant coefficients. We have 2a is equal to 1, a is equal to 1/2. Then equating all of our alpha coefficients, we have 3a alpha coming from here. Let's see, we've already dealt with that and that. 3a alpha plus b alpha plus 2c alpha is equal to 0. We know that this a is 1/2, so we can replace this with 3 over 2, divide all of our alphas out, and now we have something that we can work a little better with. Subtract a 3 over 2 over here, and we'll come back to this when we have another relation between B and C, which we can pull right out from here. We see that A alpha squared plus B alpha squared plus C alpha squared is equal to 0, or A plus B plus C is equal to 0, where A is 1/2, so B plus C is equal to negative 1/2. We can make a matrix out of this: 1, 1, 2, 1, negative 3/2, negative 1/2. This is equivalent to 0, 1 plus 1/2, negative 1, 0, 1, 1, negative 1/2. Let's make sure. I'm incredibly afraid of doing something wrong at this point because we still have a ways to go on this problem, and I would really like to do it only once. Okay, we're subtracting 1, adding 1/2. Okay, looks good so far. And then we can subtract row 1 from row 2. That's minus 1 here, plus 1 here. And we have our B and C. We see that B is equal to 1/2 and C is equal to negative 1. So grabbing this guy back, grabbing this guy back down here, we have found A is equal to 1/2, B is equal to 1/2, and C is equal to negative 1. And at this point, I'm going to pause and make sure I'm on the right track. Okay, we are looking okay at this point. So now we've split up this entire expression. Let's split up this guy. So we have 1 over alpha plus 2, alpha plus 1, and that's equal to some A over alpha plus 2 plus B over alpha plus 1. So we see that A alpha plus A plus B alpha plus 2B is equal to 1, so A plus 2B is equal to 1, and A plus B is equal to 0. We can set this guy up as a matrix 1, 2, 1, 1, 1, 0, 0, 1, 0, negative 1. And there we have it. Our A value is negative 1. Our B value is 1. And believe it or not, we are ready. It might not look like it, but we are ready to solve this problem. So ys is equal to 4e to the negative, it's not s, I'm doing alpha, negative 4e to the negative alpha over, nope, we factored that alpha in, 4e to the negative alpha multiplied by a big quantity here. That quantity is 1/2 times 1 over alpha plus 1/2 times 1 over alpha plus 2 minus 1 times 1 over alpha plus 1. And then additionally, we have what we just found here, minus 1 over alpha plus 2 plus 1 over alpha plus 1. And okay, we are ready to take the inverse Laplace of all this. So the inverse Laplace of y alpha is equal to, well, these two bits are going to be easy to deal with. Negative 1 over alpha plus 2, we can use the rule that e to the at Laplace is 1 over s minus a. And so if this a term in this case is negative 2, we can say that this guy right here, when we run the negative Laplace transform on it, will be negative e to the negative 2t. And then in the same way, right here we will get plus e to the negative 1t. And things get a little more complicated when we start dealing with our e connected components. But if we go look down here, so we can apply this rule that they give here, where e to the negative cs times the Laplace transform of f of t is equal to u1, well, uc of t in our case, it's u1, multiplied by f of t, but we replace all of our t's with t minus c. In our case, c is equal to negative 1. So we can write this as plus 4e to the, sorry, c is not negative 1, c is positive 1, because we have negative terms in both of these. Negative 4 u1 of t, and then a big quantity in here, and we're just going to do the normal Laplace inverse Laplace transforms on these three components here, but at the end we're going to replace t with t minus 1. So we have 1/2 times 1 over s. Well, 1 over s Laplace transforms back to 1. So we will have 1 times 1/2, and then we replace all of our t's with t minus 1. So that's just going to give us 1/2, and we will have plus 1/2 multiplied by 1 over alpha plus 2. Well, that's going to get inverse Laplace transformed back to e to the negative 2t. So we'll have e to the negative 2, and in place of t, t minus 1. And then finally, we will have negative e to the negative 1 t minus 1. And this is at least what an online calculator also gives me. So hopefully this is correct. I think there might be something up with the Laplace transform of 1 over s not actually giving you 1, but giving you u of 0, because this is only defined for positive s. But I'm just happy to have this done. That specific component here, I think, could easily be slightly wrong. But on the whole, I really hope we don't get a problem like this on our exam. But either way, hopefully some of this was vaguely helpful, and happy studying.